Yeah, so like these cut and paste techniques are realized by these new objects we have been working on with Joan Licata, which are called foliated open books. And there's going to be some of the other things which are joint work with Akram Alishahi, who is a PhD student of Stipschitz and mine, and Kristen Hendricks and Petkova. So the main idea of these foliated open books is very simple. Like, you take an open book, you take a surface which respects this open book in some way, and then you cut your open book in two pieces. And what you're aiming for is that eventually you want to just take one part of where you cut it open, so and describe this as an object of its own. And these are called foliated open books. And then we want to define what does it mean for a foliated open book to support the context structure. We want to prove Giroux's correspondence for them, which we're not going to, I'm not going to do it now here. And then we want to use it to prove things. And there are already two applications which are completely done. One is that you can use these foliated open books to prove that the support norm is additive for tight context structures, and then you can use these foliated open books to define contact invariant in bordered homology. They are somehow the natural objects to do it. And I have a list later, so I think there is like a lot of things you can use them for. So first of all, so the idea of what this nice surface is goes back to quite early. It appeared, the main idea appeared in a paper of Benakin, in the PhD thesis of Benakin, where he proved that the standard open book is not over twisted. The standard context structure is not over twisted. And then later, Berman and Manasco used these ideas of open book foliations for proving results about braids. And then Lafontaine recently with Manasco proved the Jones conjecture using them. And then so all of this happened in S3 with the standard context structure, with the standard open book, like the disk open book. And then recently there is a generalization of all of this for open books, for surfaces in any open books. And this is done by Ito and Kawamuro, and these are the ones we're going to use somehow. So just to fix the notations, I'm telling you very quickly what I think of a context structure. So that's a plane field in a three manifold, which is non-integrable, where the non-integrability condition can be described by this alpha wedge d alpha being a volume form in the three manifold. So I'm assuming that my three manifold is oriented, and I'm assuming that every context structure ever talked about is co-oriented. If you have a surface in a three manifold, then the contact structure prints a foliation on the surface. This is called a characteristic foliation. So this is defined by this one form, restricted to the surface. And what Giroux proved about these characteristic foliations, that the contact condition somehow descends to this. The contact condition descends to this surface to be this condition that the divergence of the foliation is non-zero at the singular points. So if you are only in my talk, I'm mostly going to concentrate on isolated singularities. So if you are only thinking about isolated singularities, and then there are two isolated singularities with non-zero divergence. One of these is elliptic points and hyperbolic points. And then, for example, these centers are not going to be allowed. They don't occur as characteristic foliations ever. Okay. And then one important thing about contact structures, that this characteristic foliation is somehow the germ of the contact structure, near the surface, and it determines the contact structure in the neighborhood of the surface. Meaning that if two surfaces have the same characteristic foliation on them, then they have a contactomorphic neighborhoods as well. An open book decomposition is a way to describe contact structures. I'm gonna call the binding by B, and then I'm gonna think of an open book most of the cases as an explicit foliation of the complement. So I'm not thinking of abstract open books, I'm thinking of open books which are embedded in the contact structure. So this pi is a fibration of the complement of the binding, and there is this extra condition that near the binding, this fibration has to look like the pages of an open book. So the fibration has to be theta in the neighborhood of the binding.
Vera?
Yep.
You have a question? Kursat, go ahead.
What is the question? I don't see it.
I wrote it in the chat. Does this surface needs to be convex, or it's true for any surface for the foliation?
So I go back. So for this to hold, you don't need the surface to be convex, but very soon it's going to be convex. Okay.
Okay. Thank you.
So
I don't know if that's the question, but in general, you might have, even with isolated singularities, you might have other types. You might have like birthday singularities. So here you assume genericity of the surface to get this.
That's
picture.
true. That's true. Yes.
Okay, thank you.
Yes, thank you, Vincent, actually. Okay, and then another way you can think of open books is really like thinking of them as mapping cylinders, so that you take the preimage of one point, you call that S, maybe the preimage of the point 0, you call it S, and you cross it with an interval, you factor out by the first return map. So like if you factor out with x1 being equal to hx0, and then you get a manifold whose boundaries is the binding cross S1. And then you factor out with an extra condition, with an extra equivalence relation, that you collapse each of the points of the binding, one point of the binding cross S1 onto one point. So xt is collapsed into xt prime for any point on the binding. Okay. So examples of open books are like the simplest example is S3 with the z coordinate being the binding, and then the theta coordinate being the angle of the half planes. And then there is this other example which people usually use. It's S3 with two circles removed, and then these two circles can be fibered with fibers who are annuli. And then in this case, the monodromy is a Dane twist along the core of this annulus, and you can also do that with when the two circles are oriented differently, and then you get an annulus, but the Dane twist is changing to its inverse. Okay, so we say that the contact structure is supported by an open book if the binding is a transverse knot, meaning that it's transverse to the contact plane fields, and if the contact structure is nearby the pages of the open book. So here nearby, you can phrase it like really like precisely. This just means that d alpha has to give an area form on the pages, and then with this notion, the examples 1 and 2 are supporting contact structures isotopic to the standard contact structure. And then there is this well-known correspondence between open books and contact structures, that whenever you take a contact structure, you can construct an open book which supports it. And if you have two open books which support the same contact structure, then they have a common stabilization. And the stabilization is really just a local operation which connects the whole open book with this example number 2, which was the annulus page. Okay. And then here comes our first example for a foliated open book. This is usually how you should be thinking of foliated open books. So you take a 3 manifold, which is embedded into another closed 3 manifold. So 3 manifold boundary, which is embedded into a closed 3 manifold, which has an open book already. Okay, and then you're looking at how the open book intersects the 3 manifold. Okay, so when you take angle 0, then the open book intersects your solid torus in this rectangle, which is sort of curved up as a telephone. And then as the time is progressing, then at some point these angles of these are going to get closer and closer to each other, and eventually they're going to get pinched off, and then you're going to get 2 half disks. This is what happens at time pi equals half, and then they're gonna again get closer and closer to each other until you attach another handle and you get back to at time pi to this telephone shape. Again, as you progress forward, you get to 2 half disks, and then again a telephone. Okay, and then you have to somehow glue these 2 telephones S0 and S2 pi to each other, but there is a unique way to identify them with each other with a map which fixes these binding components there. Okay, so there's 2 rectangles. It's identified with the identity map. Okay, and then also notice that as you did this, you got a fibration of the complement, like a singular fibration of the complement of the binding, but you also got a singular foliation of the boundary. Okay, and then let's see how this works in general. So imagine that you have a 3 manifold with an open book decomposition on it, and then you just choose a surface which is in good position. And here good position means that it's as generic as it could get. So the binding has to be transverse to the surface, and then you restrict the fibration to the surface. It has to be Morse. And then there is one more condition, which is not a generic condition. It's a condition which can be achieved by isotopy, is that the level sets of this fibration restricted to the surface cannot have closed components, so cannot have circles in it. That's going to be very important for us, and it's sort of an annoying condition otherwise. So I think that's sort of an interesting idea. So you have this pi, which was a fibration. It was completely regular, but when you restrict it to a codimension 1 surface, it could start to have singularities, and these singularities are gonna somehow look like exactly like these, or minimum or maximas. But the fact that you're not allowing circle components is going to rule out the minimums and the maximums. And once you have this surface, you can cut your 3 manifold and the open book along this surface to get an open book for just one of the pieces, or both pieces in this case. Okay, and then what you're getting is it is not such a nice object. So it's what you're getting is a fibration of the complement of whatever is left from the binding minus which has critical points on the boundary. We sort of don't like that. So what we are doing is that instead of only having critical points when you restrict to the boundary, you want to have critical points even for the function, even when you think of it as in the stream manifold. And for that, you're just going to take a neighborhood of the surface, and you modify your fibration by making canceling pair of index 1 and index 2 critical points for every critical point of the Morse function restricted to the surface. Okay, and then you're getting a foliated open book. You can forget whatever I said before. This is the definition of a foliated open book. So you have one manifold which is properly embedded in your stream manifold, and then the complement of it has an S1 valued Morse function, and then the critical points of the S1 valued Morse function agree with the critical points when you restrict to the boundary, and the level sets cannot have closed components. So this means that, so if you cannot have closed components, then you're not allowed to have minimums and maximums. So you can only have index 1 critical points for the boundary. And then this index 1 critical point, when you look at it in the whole manifold, then it has an extra dimension. It's either a descending or an ascending manifold. So it can be an index 1 critical point for the whole manifold, and it can be an index 2 critical point for the whole manifold. And here are the two examples. Like here are the two cases you can have. So either everything else is going upwards afterwards, or there is an extra dimension which is going down. So these are the hyperbolic points. And then once again, just remember that when you restrict everything to the boundary, you get the foliation of the surface. And then this foliation, we already see it, how it looks like, the level sets. This is how it looks like away from where the binding intersects the boundary. And then when the binding intersects the boundary, it sort of looks like an elliptic point. Okay, so you have hyperbolic points at elliptic points, which are exactly what we had for characteristic foliations, for generic characteristic foliations. And then that's exactly why we try to not have the circle components. And then here is the notion of what compatibility means. So a foliated open book supports a contact structure if the binding is transverse. That's the same condition as we had before, and if the contact structure is nearby the pages of the open book. And this is the first condition here, that d alpha has to be an area form on the pages. And then here's the second condition of nearby being defined near the boundary. So what it says that the contact structure, the characteristic foliation has to be topologically equivalent to the foliation given by the level sets of the Morse function to the boundary, restricted to the boundary. So well, that's not the prettiest notion. It's really a topological notion. You cannot say that these two foliations are somehow can be brought to each other by diffeomorphism, because of the divergence non-zero condition for the characteristic foliation, and the divergence is clearly zero basically everywhere except in the elliptic points for the foliation, because that's just d pi. And then
Vera? I have a question from Rohil Prasad. Rohil, go ahead.
Oh, hi. I was just wondering, this does not, I wanted to clarify, this does not imply that the binding has to be a reeb orbit, right? Or,
No.
Okay, thank you.
Yes, no, it is just any transverse node. But what it implies is that so basically the boundary after all these things, so it's a generic foliation which only has hyperbolic and elliptic points. We can also make sure that the hyperbolic points don't happen in the same time, meaning that there is no there is no saddle connection. So this is going to be a convex surface. Okay, so the boundary under these conditions is automatically convex, but there is an extra structure on it which is given by this foliation. So and then we have proved for these structures that if you have a contact structure with a fixed characteristic foliation on its boundary, and this fixed characteristic foliation looks like an open book foliation, so meaning that there is a pi for which it's the level set, then you can construct a foliated open book for it with a fixed boundary, and then isotopies of this contact structure are giving you the same foliated open book. And if you have two foliated open book defining the same contact structure, compatible with the same contact structure, then they have common stabilizations, where the stabilizations all happen inside the manifold, like far from the boundary. So you have common stabilizations which give you the same foliated open book at the end. The proof is not an independent proof of the original Giro correspondence. It goes back to the Giro correspondence for partial open books, which goes back to the original Giro correspondence. And then, so the reason usually people like open books is because they are combinatorial, and you can really define these as combinatorial objects as well here. So you just take the preimage of a time. So this is somehow what's the page, and then the boundary of that's going to be a surface with boundary, and the boundary is going to consist of maybe closed components of binding. These are like supposed to be purple if you see the colors, and then these polygonal regions which are binding and something which goes out to the boundary. So this is part of the foliation on the boundary, and then again binding and foliation and binding and foliation. And remember that we had no closed leaves, so meaning that there is no boundary component which is entirely living on the boundary. Okay, so this is how the pages look like, and then the pages, they are not constant as they used to be for normal open books, but they are changing over time. They are for index 1 critical points, they change like that, and for 2 critical points they do exactly the opposite. So you either cut along something or glue a one handle to your foliation, to your pages, and then so an abstract foliated open book can be then really defined. So it's a sequence of pages. You have to have even numbers so you can get back to the same diffeomorphism type from S0 to S2K. And then each of them have polygonal boundary and maybe some circular boundary, but the circular boundary has to be in the binding. And then each page is related to the consecutive one by either a cut or a one handle gluing. And then there is a diffeomorphism which takes the last page into the first page and fixes the binding. The binding never changed because these are all whatever is changed is on the foliation. It's near the boundary, which means the boundary of the surface. And then having this information, you can reconstruct your stream manifold. You can define these cobordisms, which are, so for each of these surfaces which are related to each other, you can define a cobordism, which is just changing as a saddle in between. Everything else stays the same, and then you again collapse the binding after you glued with the map age, the S0 and the S2K page. So this is a schematic picture. Each of these cake slices are cobordisms. Okay, and then the boundary also gets a foliation on this. Okay, and then you can very easily construct abstract foliated open books just as subsurfaces of normal abstract open books. You just take a sequence of subsurfaces of an open book, and so you're cutting and gluing, and you're making sure that that as you get to the last page, then the monodromy brings back the original open book to its the page, whatever you took as a subspace, to the origin, to the S0 subspace. Okay, so the age of S2 has to be S0. So for example, this is a part of this annulus page open book with a positive Dehn twist. It looks like this. You take the annulus page and you just take two parts of the open book and you take the ball around it. Okay, or you can construct the exact same one for the negative Dehn twist. You just have to make sure that when you're cutting, then the gluing happens in a different place, and then you are getting a negative Dehn twist between them. This is a very important idea somehow, that is Dehn twist somehow can be decomposed into these cutting and gluing pieces. And that's going to be used later. And then the whole reason we care about these foliated open books is because you can somehow use them to cut. So if you have that's basically how I defined them in the beginning. So if you have a stream manifold and you have this nice surface in the middle of it, it actually doesn't have to be a separating surface. It could be a non-separating one, it still works. Then you can remove an invariant part where you change so invariant with respect to the contact structure, but you change the foliage, the vibration to have critical points, and then you're getting two contact structures and two open books for each of the two foliated open books for these contact structures, which are actually happen to be the restrictions of the original open book. Okay, so that's the cutting, and you can do the whole thing backwards as well. So if someone gives you two foliated open books which happen to have the same foliation on their boundary, and you can glue them together, you just have to insert this standard piece which removes the canceling pair of critical points. And then this cutting and gluing can be used to prove the additivity of the support norm for contact structures. I want to talk a little bit about that because I think that's an interesting application. So the support norm for a contact structure is the minimum of the Euler characteristic minus the Euler characteristic -1 for an open book which supports the contact structure. This might be one off from what you usually think of the support norm, but it's much more convenient for me at this moment, okay? And then you want to understand how this support norm behaves under connected sum. So if you have two open books for two contact stream manifolds, then you can take the connected sum just in the neighborhood of a ball, like where everything is standard, and you make sure that this ball is that this point you take the neighborhood of is actually lying on the binding. Then even the open book part is completely standard. You remove it, and then you glue the two open books together, then you are getting a new open book for the connected sum, whose pages is the connected sum of the pages of the two original open books. Is the boundary connected sum of the pages of the two open books. So you immediately see that the support norm has to be sub-additive, okay? And then the question is whether it's additive. And then the answer is that it's not. Burak Özbakçı proved that it's that like he gave an example where it is not where it is not additive. So if you take any over-twisted contact string manifold and an integral homology sphere, then and you connect sum it with the over-twisted contact structure, which has -half the string invariant, then you get back the same contact structure because it has the same D3 invariant and is over-twisted. And then, but the support norm of this contact structure is non-zero, and then it's not additive. Okay, but so we used Eliashberg's theorem for over-twisted contact structures, so maybe it works for tight ones, and that's what I proved, that it actually does work for tight contact structures. Okay, so the statement is the following: if you have two tight contact structures, you connect sum them, then the support norm of the connected sum is the sum of the support norms of the two contact structures you started with. So why is this a cut and paste argument? It's a cut and paste argument because you do have this S2 in your connected sum, which I'm going to put in a nice position to have an open book foliation, and I'm going to cut, and then gluing something which is coming from S3, also from a cutting. Okay. So first of all, what we have seen already when we saw that the support norm is sub-additive, we have seen that if the open book foliation happens to be the standard one on this S2, then we are done. Then the support norm is automatically additive. I mean, if I had if I had an open book here, then I can construct an open book for each part of the M1 and M2, and the pages are the boundary connected sum of the pages gives you the original page. So the support norm would be super additive as well, and you would be done. Let's just see how this construction goes as a cut and paste technique. So here is your S2, which happens to have this foliation on it, and then here is your S3 with the standard open book, and then inside of it there is this another S2 with the exact same foliation, and then you cut these two pieces apart, and then you glue this part to this part, and that part to this purple one. So you get two open books which are supporting your original contact structures in the pieces from the connected sum, and the page is again the boundary connected sum of the pages. So you get that the support norm is super additive. Okay. So the problem that, I mean, one way to prove this theorem from here would be to say that, okay, but you can actually always make sure that the foliation looks like this on that sphere, but that's not true. If that was true, then the support genus would be additive, and it's not. So you can't always do that, but you can do something equally useful, is that if you have a foliation on your S2, which is coming from a tight contact structure, then it can be actually realized as a as the boundary of an embedded D3 in the standard contact structure, in the standard open book for S3. So someone gives you a foliation, then I can give you an embedding of S2 into the standard open book so that it has that foliation on it, okay? And I'm using tightness. I'm using tightness because anything which can be realized in the standard open book has to be tight. So basically the idea for using tightness is that tightness gives you the fact that the elliptic points, the graph which you can form from the elliptic points by connecting them with the separatrices is a tree. And then is a tree because its neighborhood is actually the R pass for the convex surface, which has to be a disk if it's in a tight contact structure. And then you having a tree, you can use induction. You're just removing the leaves, and then every new introduction of a leaf is going to give you a finger move for your sphere. So you originally have the normal sphere embedded as it is here, and then you're going to do finger moves as it is dictated by the foliation or this graph of the foliation, and you get your embedding. And then using this embedding, you can prove the additivity with the support norm. So you have your S2 here, which has this particular foliation coming from a tight contact structure because the connected sum is tight. Right? Connected sum of tight contact structures is tight. So this one has a foliation, and then that foliation, just by the previous lemma, can be realized as an embedding in the trivial open book of S3. And then you again do the exact same regluing argument. So you take these parts and you take, you take these parts and you glue them together, and you're getting an open book for the closed M1C1 and M2C2. You're getting an open book, and what is the relation between this open book and the original open book of F? Well, so the original open book for M was glued together from this purple open book and the blue open book, and then you change the blue open book with the green one. So this one here, this one gives you the page of MC. They are glued along not one component as in the earlier case. So it's not a boundary connected sum, but it's glued along some interval components. And then this one is pages for this is actually the disk pages of the standard contact structure, and these are the new pages of M1C1, and M2C2. Okay, and then the other characteristic of these two sides, because it's just rearranging and everything happens along an interval, is the same. The sum of the other characteristic remains the same, and then that gives you the support norm is subadditive, because you just rearrange this one is 1, and then you get that the C of S plus 1 equals C of S1 plus C of S2, and you're done. Okay. Another application. Is this a 45-minute talk? Or a 50 or?
You have the full hour.
Full hour, perfect. Okay. So another application is to define contact invariants for contact. Sorry. So it's to define contact invariants for bordered three manifolds using this foliated open book. So just a reminder, as a black box, contact invariants have been defined for closed contact three manifolds. They are giving elements, they are taking an element in the Heegard-Floer homology, and then you can also define them for contact three manifold with convex boundary. This is a result of Honda-Kazin and Matic, and they are living in sutured Floer homology. And then what we are doing is that we are trying to define this for three manifolds with a given foliation on the boundary. These are still convex, but there is this extra information on the foliation, and we are trying to define it in bordered Floer homology. So when we are saying bordered Floer homology, we have to have a parametrization of the boundary surface, and this parametrization is secretly given by the foliation. The foliation, you can think of the foliation as a parametrization as well. Basically, the parametrization is a handle decomposition of the boundary, and then foliation is also handle decomposition because you have the elliptic points. Those are corresponding to the zero handles, and then you have the hyperbolic points which correspond to the one handles, and then the negative elliptic points are corresponding to the two handles. So, and what we have basically proved by now is that you can define these invariants in bordered Floer homology, and then these invariants do what you would want them to do. So they glue nicely. So if you have two contact string manifolds with foliated boundaries, which have the same foliation on the boundary, then you can glue them together, and then the bordered Heegard Floer homology also glue together with the derived tensor product to give you the chain complex for Heegard Floer homology, and then the contact invariants derived tensor together to give you the contact invariant in Heegard Floer homology, or the chain element in the contact invariant in Heegard Floer homology. That's somehow automatic from the construction how we do it, and then it's also related to the sutured invariant. So Rumen-Zarev has a map from the bordered Floer homology to sutured Floer homology. This map is defined by capping, by gluing a cap which somehow forgets the bordered information and remembers the sutured information. And then we can prove that the contact invariant is mapped under this capping map, is mapped to the sutured invariant for both structures, for both CFA and CFD. And then we can basically use a recent result of, someone knows the name of, so Shea's two student, David Shevelovic's two student, just recently proved that that there is this commutative diagram without the contact invariant, and what we can prove is that the contact invariant fits nicely into this commutative diagram. So meaning that the contact invariant, we know that they tensor together to give the contact invariant of the closed manifold, and then each of them, just by the previous lemma, maps into this into the sutured manifolds, and then there is this map of Honda-Kazes and Matic, which is mapping the tensor of these sutured invariants injectively into Heegard Floer homology, and then these maps, everything commutes in this diagram, whatever is drawn. So I think, so I'm not sure everyone agrees with me, but this map, the way this is defined, it doesn't really give you a way to compute it. Somehow it contains this interesting notion of like being sufficiently complicated. And then I did try to compute in particular like really simple cases, and I did not manage to. And and then, I mean, because somehow this is sufficiently complicated, is not practically checkable. And the OR definition is more complicated, that basically everything it does is that it makes this sufficiently complicated something which is checkable. Okay, I mean, that's somehow the whole idea. And otherwise, I think the map which Honda Kazis and Matic defined is really the same, like on the notes. If you just, we made it somehow, like put it in the framework of bordered Floer homology, which is somehow like something which you can use if you want to actually glue things together. And then, so the idea for the contact invariant in this bordered Floer homology is that you can, you take this foliated, this three manifold with a given characteristic foliation on the boundary, and then you construct a foliated open book for it. You construct the abstract in an abstract way, and then from this foliated open book, you're trying to define a bordered Heegaard decomposition for it. And the bordered Heegaard decomposition looks like exactly how it usually does for contact invariants. It takes a tiny piece, like interval cross one of the pages, and then the rest is going to give you the whole other manifold. The main point is that somehow each of these sections here are secretly really cobordisms, and then there are these parametrizations on the boundary, which are just the ascending and descending manifolds, and these parametrizations are just flowing down to the Heegaard surface. And that's exactly what gives you the bordered Heegaard diagram. This Heegaard diagram, for technical reasons, is going to be a beta bordered Heegaard diagram. And then, so one not so nice aspect of the whole thing is that somehow this invariant, like where the invariant lives, depends on the time parameterization. So remember, there was so you had a fibration on the foliation on the boundary, but this foliation included the extra information having this that it's a level set of some Morse function. Okay, and then this is somehow included in the whole picture. Basically, you have to choose a time zero, and that's what's going to give you the base point. It's going to be a base point is going to be the neighborhood of the time zero leaves. So the bordered picture depends on this, like in which bordered Heegaard diagram it leaves depends on the in which bordered Floer homology leaves. The contact invariant depends on where time zero is. Even the Heegaard Floer homology it lives in depends on the time zero. So what we're gonna do next time, what we are working on right now, is to prove that that there is a nice cobordism map which maps one to the other. Okay, so that's the next step, that it maps one to the other, and it also gives a Morita equivalence between these bordered Floer, between the bordered Floer algebras. Another things you can do with these foliated open books is like go a little bit farther with what Rumen-Zarev did. So he managed to describe the homology of the bordered Heegaard Floer homologies using only sutured Floer homology. Okay, and then he conjectured that the A-infinity maps can be also described by gluing standard pieces. And I think this all setup has to give you this conjecture that this is true. Okay, and then what I'm working on currently now is that also I think foliated open books are going to allow me to give a completely combinatorial proof this already existing theorem of Alishahi, saying that if you have a Steinfillable contact string manifold, which happens to be a connected sum, then it is actually the boundary connected sum of two Stein fillings. Okay, so his argument uses holomorphic curve filling techniques, and my argument is going to use graphs and nothing more. And I think this is a feature, but people can argue on that. And then, yeah, and there is another thing I think that this whole foliated open books would actually give you a good guess of what bordered ECH should be, because somehow the map between Haygat for homology and ECH is using open books, and the one direction of this map can be generalized, I think, for this foliated open books. You would get a guess, and I'm not promising anything more than that. And I think that's basically it. Thank you for your attention. If you have questions, I'm happy to answer.
Great, let's thank the speaker. Thanks so much. Before we take questions, I just wanted to post two links as usual in the chat. The first one is speaker suggestions, and the second one is feedback for us about the seminar. All right, so are there any questions for the speaker?
I have one question. So do I understand well when you say that so this invariant should depend on the characteristic foliation of the contact structure on the boundary, not only on the dividing set?
Yes. Yes, I'm already where it lives depends on the characteristic foliation. That's why.
This is very flexible. I mean, the characteristic for foliation by the contact structure is.
Yes, I mean, you could change it and then you would get a different invariant. In fact, I mean, that's what basically I mean, we don't yet have it completely, but so that there is this underlying sutured invariant, which is mapping to each of these different characteristic foliation invariants with the right caps. So it's some sort of, yes, it's yeah. I don't know what to say. I really think this has to be the right notion for where what the bordered contact invariant should be an invariant of.
The characteristic foliation that is drawn by the open book is much more rigid than the characteristic foliation of the contact structure, because you impose of having no centers and everything. So in some sense, you have a kind of minimal foliation, whereas for contact structure, you can easily add things which are not really significant. So
yes. So this is more rigid. What the foliation can be on the boundary. It doesn't give all characteristic foliations by far. Though I mean, I have been working on trying to recognize the characteristic foliations which arise this way, like by an algorithm or something, and I don't know how to do that. It looks like a hard problem. So I mean, it's a completely combinatorial problem. You want to find basically you're trying to find the order of the hyperbolic points if someone just gives you the drawing of the foliation, and I can't do that. Like I don't even I have already examples of foliations which are not like that, but I don't see what makes them not like that.
You have a question from Kyler. Kyler, go ahead.
Yeah, I missed what you said at the end about bordered ECH. Maybe you could just elaborate a little bit on this intriguing comment.
Yeah, I mean, I don't. So I mean, this is not a precise statement at all. What I'm claiming is that I think this. So this. So there is this map which brings Hegardt homology to ECH. Is it the other way? So, which is just this map. Okay, so here on the bottom, you have surface. You have the three manifold, like S, with the. So over every point you have the surface, or the open book surface, and then here you just have a surface cross interval somehow. Okay, and then when you go around, you glue it with the monodromy. And what I'm claiming that on this picture you can just plug in foliated open book just as well, and then you're going to have S0 here and S2K there, and you will get something of what it should be. And I'm very far from being like even anyone who understands this right. But I really feel that you could derive something from this construction. It would basically give something like that you're counting reeb orbits, which are you're counting closed reeb orbits, and you're counting some sort of reeb orbits which are going between these bordered arcs. So you're going to count closed reeb orbits and reeb flows between the bordered arcs. That's going to be the generators, and then I don't know what the map is. Yeah, and it's not going to get better what I'm saying. Sorry. It's just a feeling.
Thank you.
Sorry. I would actually be really happy to talk about this with someone if someone cares, because I really think there is something in it, but I don't understand enough the ECH construction. Yes.
Are there any other questions for the speaker? I had a question, kind of maybe a more basic question. When you talked about the support norm, I was wondering, do you use that norm to think of like a topology on the space of these closed contact manifolds? Like in what sense would you use the support norm?
So why is it called a norm?
Well, what do you, let's see how to phrase it. Do you use the fact that it's a norm to help you understand these foliated open books?
No. It's really just the name of it, I think. I don't even know why is it called norm.
Okay.
No, I mean, all I'm using is that, what I'm using is that the Ala characteristic has this property that if you glue along things which have trivial which can be subtracted to the point, then this has this like nice property that say A union B equals CA plus CB minus CA intersect B if the intersection is nice. That's what I'm using.
Okay, thank you.
And in my case, the nice is like interval, actually rectangle.
All right. You have a question from Austin Christian. Austin, go ahead.
Hi, could you say something about how the combinatorial proof of Eliashberg result would go, the one about fillings of connected sums?
Yes, I mean, it's not done. So the idea is that you, okay, just start a new page, maybe here. The idea is that you are taking your stand filling, which you're thinking of it as a Lefschetz vibration, and then on the boundary, someone gives you this surface. So you have this S2 embedded into the boundary, and then you're making this S2 again to have a foliated open book foliation on it, and then so what you're basically going to have is that you have your surface, which is just a fiber surface. Okay, so this is a fiber, and then it's separated by how the S2 intersects it into, okay, it's really hard to draw anything which separates. Yeah, so I don't know, that separates. So this is somehow, yeah, so this part here is M1 C1, and the rest is coming from M2 C2, and then you know that every time you cross a critical point of this Morse function, somehow this one is changing by maybe cutting it along something or gluing something on one handle on the other part. Okay, and then what I'm trying to do is that somehow sometimes, and I think in this case you will always gonna be able to like somehow pair these cutting and the gluing arcs in a way exactly how it was in this picture. Wait a sec. In this picture. So each of, like, you're gonna have a paired arc, each of them giving you a Dehn twist. And then again, I'm gonna use that Dehn twists are all positive to deduce that these are actually have to be corresponding to Lefschetz, to one of the, sorry, I'm gonna find where am I? So it has to correspond to one of the Lefschetz, so one of these Lefschetz critical points here. So what I'm saying that you can pair the cutting and the gluing ones so that they give you a Dehn twist, and this Dehn twist actually is one of these. Okay, I'm almost done with that section, that notion. And then once you are done with that, then you're gonna be able to like somehow fill in this this S2 to be a D3 inside your over the entire Lefschetz vibration. And then that I understand too. What I don't understand is that, so this is smoothly cutting it up into two four manifold. I don't see that they are stand fillings of the whole thing, but that's mostly because I haven't tried it yet.
Okay, that helps. Thank you.
Yes.
Can you use this to define the relative versions of like similar to loss invariants?
Like,
You're defining contact invariant and Haggard Floer using this cutting up through the border Floer. Can you do the same for loss, like Legendre invariants?
angles, yeah.
You can do it.
Yes, you can do it. It's just, yes, you can probably do a tangle invariant, which is gluable for Legendre tangles. I mean, you could do that for sutured as well, and no one did it. I mean, I actually tried, but then I didn't see why was it useful. And here I also don't see, though maybe the glue abilities makes it a little bit more useful than the other one, because that one is like, somehow you couldn't specify how you glue together things, and maybe here you could. So, yes. Any other questions?
I had one more question. Does it make sense to talk about this support norm also in higher dimensions? And is anything known about like subadditivity or additivity?
Oh, I have no idea. I don't know.
I guess you could ask not just for connect sum, but also for higher surgeries too.
I mean, you can. Yes, you could. Even here, you could ask for somehow cutting out something standard and then gluing a new thing. So I've been thinking how you would take these foliated open books to higher dimensions, and there is some hope, but that you can do it. But it's so I'm not very deep in this project, and I think it's somehow first you have to understand that so here you had to make a trick to rule out some of the singularities. So there were these more singularities. There was the centers, which you had to rule out to even be like characteristic foliations, and then characteristic foliations for higher dimensional surfaces are like somehow less. I know Young has a paper about it, which I'm looking at. And then if you understood those singularities, and that you could like pair up the singularities, then maybe there is some hope that you can do something similar.
Otherwise, I think support norm in higher dimension should be, so in higher dimension, the page is a Weinstein manifold, and the support norm should be the minimum number of n handles, I mean, half-dimensional handles for a Weinstein page, which is, I mean, which generalizes the other characteristic in some sense.
Mm-hmm.
I'm not sure anything is known about this.
I see, but you're saying it's more natural to use the number of n handles than like just the Euler characteristic.
Yeah, probably, yes.
But why? Why? Or just?
Yeah, I mean, critical handles are the one to look at in higher dimension, I think.
Okay, I can believe that.
Let's see, I had one more question, if that's okay. I was wondering if you could elaborate a bit more on the connection to sutured invariant page. You mentioned that this map is, a definition of the map includes sufficiently complicated, and that you're able to get around that, or you're able to compute with the diagram. I was wondering, could you say a bit more about what the sufficiently complicated part is and how your work allows you to do concrete computations?
I mean, my work allows to do complete computations as long as you can do any type of computations in border. I mean, like, so, and then it's sufficiently complicated somehow. So what they are doing, so that you have so you have a partial open book for your for one of your three manifolds, and you have a partial open book for this other three manifold. So like this is M1 and this is M2, and then when you glue those together, you will not get the partial open book of the big manifold, because somehow it's just wrong. You have small pages, and the small pages wants to go to big pages, and it just doesn't work out. So what they are doing instead of that is that somehow they are putting in a piece in the middle, which is somehow makes this gluing possible. So this piece is just a surface cross interval. Okay, which makes this possible. I mean, and then this surface has to be somehow. I mean, this one has a Hegel decomposition as well, which is coming from a Legendrian handle decomposition, from a Legendrian graph. And then this graph has to be complicated enough so that somehow when you have a holomorphic disk here, and this part you have a holomorphic here, then that cannot somehow flow into the other part. Okay, they are using that even to define the map. And then what we are doing is that we cut this in half, and then what's in the middle is exactly a foliation. And then we define an invariant for this part, and we define an invariant for this part, but they are living in border for homology, and then they glue nicely together. So we tell what do you need for the bordered for the holomorphic curve not to be able to go over there, because here it won't be able to go there. So it's going to be like every bordered invariant, every holomorphic curve which starts here might go out there, but then it's going to stop in this part. So that's it.
I see. That's cool. Thank you. All right. Unless there are any further questions, let's thank the speaker again, and then we'll go into the discussion session if you'd like to stick around and talk some more. Okay, so let's thank Vera again.